My goal is to present statistical and machine learning material as well as other data science related concepts in a way that's easy to understand. Material in video format is easy to digest, and this way I can show diagrams, animations, and step-by-step math derivations to support the information being presented. I find it easier to digest the what after having been presented the why. Therefore, another goal is to present concepts first before going into details. However, note that a lot of the content being discussed goes deeper or can be viewed under a different lens when it comes to interpretation and how the ideas tie back to different fields of study. Lastly, I'll try to do my best to present all of this information in a way that ties new material to already covered topics. This should hopefully give the viewer a coherent big picture view of the material. Why might we want to use machine learning? What is the motivation for using this tool? We may be interested in making better decisions or partially automating or speeding up certain processes. This can lead to direct savings in terms of money and/or customer satisfaction. For example, in the case of deciding what to recommend, making better recommendations retains customers. There are cases where we try to just gain some insight into data that we already have. One common example would be to see if there are useful groupings of the data via some sort of clustering. Lastly, there may be cases where the data itself is not in some structured form. We can try to use machine learning to make that data more usable. For example, a self-driving car might use a video camera to collect information about its surroundings. However, we probably want to extract the locations and identities of objects around the car and decide what to do next based on that, instead of dealing with a raw video. There are many more situations and reasons to use machine learning, but hopefully I've given at least a few compelling reasons for its usefulness. The astute viewer will probably have noticed that I use the term data without defining it. A lot of people probably have an intuition for what data is at some level. The definition on Wikipedia is something around the lines of facts, statistics, or items of information. Data points are individual items of data. There's a wide range of things we can call data, but here are a few common types of data. Tabular data is data in table format, usually with individual rows containing information related to a single item of interest. Data in text form can be words, sentences, articles, movie reviews, etc. Some examples of audio data are calls and music. Images can be pictures of any kind, while video is usually a sequence of pictures, sometimes with accompanying audio. A dataset is a collection or set of data. Here, I show a set of images of either cats or dogs. If each item in the set is accompanied by the things we want to predict, we call the dataset labeled, where the labels are the prediction targets. For this example, we may be interested in determining whether the image contains a cat or a dog, and since each image is paired with the answer to that prediction, this is a labeled dataset. One early dataset for handwriting recognition is the MNIST dataset created by Yann, LeCun, Corinna, Cortes, and Christopher Burges. This dataset contains thousands of labeled images of handwritten digits from 0 to 9, each image accompanied with a label indicating which number was written in the image. Let's now introduce some mathematical notation. We'll use this blackboard bold X to indicate a distribution of data, while little x with an index, I in this case, sampled from that distribution is an actual data point. We can also have label data points where we use letter Y to denote the labels. We'll denote a dataset with a D, and we can use the indices on the data points to write the following as shorthand for the labeled dataset. So far, we have datasets that contain data points, but not all datasets are labeled. In the case of MNIST, we probably want some automatic process to map handwritten digits to numbers. In general, our goal is to take data and learn some useful function from it. Most frequently, we want to learn function f sub theta that can take inputs from data distribution x and produce values from some output set. We call this function a model. Parameters are the set of values which influence a function's output, and the goal is to set them such that the model does its job of mapping inputs to predictions well. The process by which we find good values for our parameters is called fitting or training, but I'll leave the details for another time. As we just discussed, theta is the set of model parameters. Let's look at an example. But first we'll need some data. Suppose our task is to take data on this xy plane and learn a model such that we can plug in any x value and predict the corresponding y value. One way to do this would be to fit a line y equals mx plus b. When doing so, we can treat m and b as parameters. This gives us a way to control slope and intercept. Here, we have a fixed set of finite parameters, and therefore we call this model a parametric model. There are also classes of models and algorithms that are not parametric. Suppose for a given x we want to make a prediction for, we take the 5 nearest points on the x-axis and average their y value. For another prediction, we might use another subset of our data. We still have finite number of subsets for this particular amount of data to use for prediction, but if we add more data, we need to keep it around to make predictions. So our procedure grows with the amount of data. This is an example of k nearest neighbors with k equals 5, meaning we use the 5 closest neighbors, in this case points, to make our prediction. It's technically an algorithm, but it does give a simple illustration of something being non-parametric. To finish, we'll give an overview of different types or areas of machine learning and some intuition about what kinds of problems they deal with. First, if we have a dataset with labels and we want to use it to learn a model to predict the labels given inputs from data distribution X, this is called supervised learning. The data is used as gold standard or reference to train the model. Thinking back on our MNIST example, we would use our label dataset to learn a model, which predicts a number given the image. If we don't have labels, we might try to still find useful structure in the data itself through clustering or some other process. This is referred to as unsupervised learning. If we have a mix of labeled and unlabeled datasets and we try to use them both to learn a useful model, we have semi-supervised learning. I'm also including self-supervised learning since it is a term you may come across fairly frequently, and it generally refers to the process of doing supervised learning but instead constructing labels for each data point from the data itself, and usually on the fly. For example, we might mask out certain words in a sentence at random and try to predict the missing words. Here, the missing words act as labels. We might also distort an image and see if we can determine if the two distorted images came from the same original. As you can imagine, these tasks are difficult, and doing well at them means being good at understanding language or good at interpreting visual inputs. You may also hear the term reinforcement learning, which is fairly different from what we have discussed so far. It involves allowing an agent to explore an environment and learn from its experiences to maximize the gathering of some reward. For example, we can let it try to discover how to maximize the number of points gathered while playing a game, but I'm not going to go into too much depth there.